Good afternoon, everybody. My name is David Frater. I'm the interim director here at the Bank Observatory. Welcome to our community Zoom. Just a couple.
Dave, we've lost your audio.
What did I do? Oh, when I clicked the button. Thank you, Paul. I'm sorry. Welcome everybody to the community Zoom. When I must have, did you lose it, Paul, when I switched slides or?
I'm not sure exactly when, but you just dropped off. Carry on.
Okay. Anyway, just a few notes on the Green Bank Observatory. We have a public eclipse viewing party at the observatory on April 8th. Our summer maintenance, we've been advertising this, will be down more this summer than normal because we're doing infrastructure improvements. We're replacing wheels, some of the wheels, and also doing foundation track repairs. Just coming down the road, there are plans to put an NGVLA low elevation prototype antenna will be coming to the observatory in the coming years. So that's things in the future that we're working towards. So I'm going to go hand it over to Jay, who will introduce our speaker. Jay, take it away.
Okay, thanks, Dave. Our speaker today is Patrick Taylor from NRAO, who's going to be talking about planetary radar using the GBT. And let me just remind everyone, this is being recorded for your future viewing and will be accessible through the Green Bank Observatory website. And if you have questions, please submit them through the Q&A button on the bottom, and we'll get to those when Patrick finishes his presentation. Go ahead, Patrick.
All right. Hi, everyone. My name is Patrick Taylor. I'm the radar division head here at NRAO, and I'm also the project director for the next generation radar, where we're looking to put a high-power transmitter on the Green Bank telescope to be the next high-power radar system for the country. So GBT has been used in planetary radar since its inception, obviously as a radar receiver. This includes over 20 years of participation in radar experiments. In fact, two of the first science observations ever done with the GBT were radar of Venus and a near-Earth asteroid, where Arecibo Observatory transmitted and Green Bank did the receiving. And this has continued for the last 20 years, off and on doing various receiving for radar projects. This includes, actually, we were observing with Green Bank just last week, observing an asteroid with Goldstone transmitting and Green Bank doing the receiving. One of the big results that's come out of using GBT for radar receiving was confirming the success of the NASA DART kinetic impactor technology demonstration. So if you're not familiar with the DART mission, it was a spacecraft sent by NASA to a binary asteroid called Didymos and Dimorphos. And the DART spacecraft was smashed into the smaller asteroid, Dimorphos, to see how much a kinetic impact by a spacecraft could affect the trajectory of an asteroid. So on your right here, you have radar images taken with Goldstone transmitting and Green Bank receiving. And these are images of the binary asteroid system. Radar images are a bit strange. The dimensions here are range from the observer increasing downward. So your transmitter is coming from the top of the image and going down. And then the horizontal dimension here is speed instead of necessarily position. Now the smudge here in the middle, that is the larger asteroid Didymos, and then Dimorphos is this bright pixel in green. And if you were to follow it through its orbit around Didymos, it would trace out this ellipse here. Now, the whole point of the DART impact was to try and move Dimorphos. So the green is where we observed Dimorphos. The blue here is where it should have been if it was never hit by the DART impact. So the radar images soon after the impact happened conclusively showed that a change had happened to the system. And this has been reported in Nature last year. There's also a paper that just came out in the Planetary Science Journal describing how the orbit of Dimorphos was changed by the DART impact. And it's really neat that radar was able to help confirm that. So GBT has been great as a radar receiver, but we also want to take advantage of it as a transmitting station. And a lot of this comes down to antenna gain. We have a 100-meter aperture on the GBT, which translates to gain. We have an incredible surface accuracy, which translates to gain. That means we can go to high frequencies, which translates to gain. So all this together means GBT is a very attractive place to put a transmitter. And furthermore, GBT is fully steerable. It can see 85% of the sky, so that's a large improvement over something like Arecibo, which could only see about 1/3 of the sky. And if we can put a transmitter on the GBT, this will complement Goldstone, which is the only remaining planetary radar system after the unfortunate collapse of Arecibo. So this would be a chance to give us some redundancy and some complementarity to the planetary radar at Goldstone. So we want to do our receiving with the very long baseline array. So instead of receiving with just one telescope, we're going to try receiving with 10. So this is something we call multi-static receive, where you have many different receivers working together. So the very long baseline array, or VLBA, is 10 25-meter antennas that span from Mauna Kea in Hawaii across the continental United States and to St. Croix in the US Virgin Islands. And the headquarters, or all the data, essentially goes back to Socorro, New Mexico. And in terms of what the antennas look like, they look similar to Goldstone or the other antennas that are part of the Deep Space Network, but they're smaller at 25 meters. And of course, they only receive, they don't have transmitters on them. And they have also been used for radar, although in a more limited way than compared to the Green Bank telescope. So what we want to do is put a transmitter on the Green Bank telescope, and back over the pandemic, we actually had a small pilot transmitter put on the Green Bank telescope. So this was done through a partnership with Raytheon, and on the left side here, you can see the transmitter equipment put inside a prime focus housing from the Green Bank telescope. So the transmitter is relatively simple. It has amplifiers in it. It has a waveform generator, power supplies, and it was packaged up by Raytheon, sent over to Green Bank, where a pointing receiver was put into it, as well as a feed horn, and it was then mounted at the prime focus of the GBT. So here's a zoom in of the transmitter at the prime focus. It's the little box here, if you can see my cursor. As I said, built by Raytheon, mounted at the prime focus. So the transmission came from this little box off the primary surface of the GBT out into space, bounced off its target, and the echoes were recorded with the 10 antennas of the VLBA. Now, the system has several differences compared to previous planetary radar systems. So one of the main ones is it makes use of solid state amplifier technology. So this is essentially something called mimics. So essentially a bunch of small components working together rather than sort of a large monolithic component like the klystron amplifier tubes that are used at Goldstone and were used at Arecibo. So this is something that hasn't really been applied to planetary radar before. So we're testing that out. The transmitter frequency was 13.9 gigahertz at KU band. So here again, we're making use of the surface accuracy of the Green Bank telescope to go to a higher frequency than is typically used in planetary radar. So just for reference, Goldstone operates at 8.56 or X band, 8.56 gigahertz in X band. Arecibo operated at about 2.4 gigahertz or S band. So this is a lot higher frequency, especially compared to Arecibo. And this is a proof of concept transmitter. It was meant to be low power just to see what we could do. The output power was a whopping 700 watts of continuous output. So if you compare that to the microwave oven in your kitchen, that's about half the power of your microwave oven. But you'll see we can do some really amazing things even with that low power. And the waveform bandwidth, which essentially gives us our resolution in the radar images, was up to 200 megahertz, which gives us roughly 1 meter resolution in some of the images I'll show in a moment. So as I said, this was done during the pandemic. There were observations done in November of 2020 and March of 2021, and some of the targets included sites on the moon, as well as a near-Earth asteroid. So enough preamble, let's get into pretty pictures. So on the left here is a series of radar images of the Apollo 15 landing site on the moon. Each frame that you see in this animation is about a 1-minute integration, and there's 100 or so frames in here. And it's essentially, I'm calling it a spotlight radar image because in this case, our beam size is a lot smaller than the moon. So it's essentially looks like you're shining a flashlight on the surface of the moon. So the brightness you're seeing, that's literally the radar illumination of the beam pattern of the moon. You might even see that it kind of jitters a little, which might actually just be vibrations in the GBT causing the beam to bounce around a little bit, say by just wind blowing on the feed arm. And so you can see there's motion happening in this. The scene is not still. That's because of the Earth's rotation, the moon's rotation, the translation between the Earth and the moon. So if we want to make a really detailed image, we need to account for that motion that's happening in the image. So if we can take care of that motion compensation, we get an image like this. So again, this is the Apollo 15 landing site. Apollo 15 landed in the region just to the left of the Hadley Rill, this sort of snake-like feature. So the landing was just to the left of that. So the native resolution of this image is 1.25 meters per pixel. So that means the resolution is similar to optical cameras on lunar orbiters. So we're approaching resolution from the ground that's comparable to the resolution from cameras in orbit around the moon. So of course, this makes these the highest resolution images of the moon ever taken from Earth. And as I said, you need to do motion compensation to instead of having 1-minute integrations, you can have much longer integrations if you can account for all that motion that's happening. And what was found to cancel out all that motion was compensation down to about 8 microns per second squared in terms of accelerations happening within the scene of the radar image. And this is really pushing to the fidelity of dynamical models, which has been very interesting. So another point here is with this resolution, this image is humongous. It's 25 gigapixels. And say you wanted to print this out for a conference and you wanted to print it at journal quality, you would need a piece of paper about 18 by 10 meters in size to print it out. So we didn't only look at Apollo 15. Another thing we looked at was Tycho Crater on the moon. So there's a radar image here on the left of Tycho Crater. Just for reference, it's about 85 kilometers in diameter. The resolution here is about 9 meters per pixel. And we can compare that to optical images. So on the right is an image from the Lunar Reconnaissance Orbiter of Tycho Crater. And they obviously look very similar because they're images of the same thing. But radar does work a little differently. Of course, the optical image is you're literally overhead of Tycho Crater and take a picture of it. The radar image, you have a different point of view and you have to reproject it to kind of get this feeling that you're looking at it from above. But you can see very similar geology between the two pictures. Maybe the main thing that sticks out will be what the central peak looks like. It doesn't look the same in optical and radar, and that's an effect called layover. Essentially, things that have altitude in a radar scene will tend to lay over and look like they're at a different distance from you. And that's just essentially a projection effect of the radar. But one thing we're working on is seeing how we can leverage having multiple receivers looking at the same scene to back out that projection effect and turn this into a 3-dimensional image rather than just a 2-dimensional image. Now, another thing I want to point out is in the optical images, the floor of the crater, especially in the region of my cursor, looks really smooth. But when you look at it in radar, we'll just zoom in a little bit. Look closely at the floor of the crater, and we'll zoom in again. The floor of the crater in the radar is not smooth. Instead, you see what I've been kind of calling like bike tracks. If you rode your bike through mud, you kind of get these linear or polygonal features all over the floor of the crater. And this is not really visible in the optical data. So this is suggesting that the radar is actually picking out geology that's been buried beneath a thin layer of dust or regolith in the floor of the crater. And this is because the radar is penetrating through that thin layer more efficiently than optical wavelengths can. So we didn't only look at the moon, we also looked at a near-Earth asteroid. So in March of 2021, there was a close flyby of Earth by an asteroid called 231937 2001 FO32. It's defined as a potentially hazardous asteroid, but that's based on its estimated size and how close it comes to Earth in terms of how close its orbit, seen here on the right, can come to the orbit of Earth here in the blue. It does not mean that it's actually posing a threat to Earth at this time. It's just a definition based on size and proximity. But it came about 5 or 6 times the lunar distance to Earth. So this was a pretty close flyby by a reasonably large asteroid, about 1 kilometer in diameter. And in the end, we were able to detect it when it was more than 2 million kilometers away with only 600 watts of power. So this spectrum you see in the bottom left, the spike here is a detection of that asteroid. This obviously is not as spectacular as the lunar images, but there's still a lot of information that you can get from detecting an asteroid like this. The position of the spike within your spectrum tells you something about how fast the object is moving. If you can measure that very precisely with radar, and this is complementary to plane of sky optical images that determine the position of the asteroid. Radar gives you an orthogonal data point there that's telling you how fast it's moving when it's in that position. We can also figure out how far away it is very accurately with radar, and those are powerful tools for orbit determination, reducing uncertainties on the orbit. And if you can do that, you can learn where an object is going to be in the future by predicting its trajectory further and further out, decades or even centuries into the future. And if you can do that, you can estimate whether it poses a threat for an impact on Earth. Now, it's not just the position of the spike that gives you information. If you were to zoom in on the spike, you would see that it's broadened. It's not a delta function. It has some width to it. And that broadening is based on how large the asteroid is and how it rotates. So you get information on its dynamical state from radar. The strength of the spike has something to do with how big it is and how reflective it is. You can determine whether something is made of metal or if it's made of rock. You can estimate things like density, material properties, and so on. So even though this is not as spectacular as the lunar images, it really shows that radar can provide you information that can help you calculate, monitor, and even mitigate Earth impact risk. So it's a very strong method for getting information for planetary science and planetary defense. So hopefully I've shown with these images that we've demonstrated some pretty compelling results of using a transmitter system on the Green Bank telescope. This has potential for meter scale imaging of the moon from the ground, which has not been done before. This can be used for geological studies like I showed for Tycho Crater, could potentially be useful for dynamics because, as I showed, we had to do motion compensation at very extreme accuracy. So that could potentially be dynamically interesting for the state of the moon. While I didn't talk about space debris specifically, if we can do this sort of work at the moon, meter scale imaging and such, we should be able to extend that to detecting, tracking, and characterizing space debris in cislunar space. So potentially we could be doing meter scale imagery of space debris. And this is going to be increasingly important for safety and security in the future as there's more and more payloads going to the moon. There's boosters, propulsion systems, and small sats, large sats, and eventually humans on their way to the moon. We're going to want to be able to track those things and make sure that they're not posing a risk to other payloads that are on their way to and from the moon. And I showed you that we can detect, track, and characterize a near-Earth object, and this is important for planetary defense, especially impact hazard assessment and mitigation planning. And if we can do this for the moon and near-Earth asteroids, we can certainly apply it to other solid bodies in the solar system for physical and dynamical characterization. So we could look at Mercury, Mars, Galilean satellites, main belt asteroids, comets, interstellar objects if one was discovered and reachable by the radar, and so on. So an update kind of where we are with the project. So the ngRADAR project has been funded through the National Science Foundation's mid-scale research infrastructure. We have an award that goes through this fiscal year that's been for the concept design of a high-power radar system. So our goal is to have a multi-static, meaning green bank transmitting and the VLBA receiving with up to 10 antennas. We want to have a high-frequency, high-power, solid-state deep space radar. Nominally something like 500 kilowatts at 13.7 gigahertz. And we want to apply this for planetary science, planetary defense, and space situational awareness. So I've shown you what we could do with the proof of concept low power system. We want to scale that up by about 3 orders of magnitude in power. We have the potential to go to even finer resolution, so essentially sub-meter resolution for the radar images. And we want this to be a rapid response system. We don't want this to be a campaign system where we have to mount all the hardware and dismount all the hardware and only use the system in a campaign mode like that. We want something that if a new asteroid was found and we needed data on it as soon as possible, we want to be able to deploy this system and be on the sky tracking that object within hours or days rather than days or weeks in a campaign mode. And we also want this to have near real-time feedback and on-the-fly data reduction. These are standard at Goldstone and previously at Arecibo. With radar observations, you really don't often know a lot about your target before you look at it. So you want to be able to get that feedback of what the radar is seeing and evolve your observations as you're doing them to maximize the scientific return you get out of them. Now, we have made a few key decision points along the way. We were considering different transmitter frequencies, going as high as Ka band, say like 35 gigahertz. But we've eventually settled on Ku band, centered on 13.7 gigahertz. The higher frequencies, there are some considerations like weather and things like that. But really, it comes down to the current technology for the amplifiers. They just aren't as efficient at the higher frequencies yet. So say we did go to Ka band, we would probably need a few times more prime power coming into the system, and then we'd have to waste a lot more heat due to the inefficiency of the amplifiers, and they would require probably an order of magnitude more components to build the system than it would take at Ku band. So we've settled in at 13.7 gigahertz. The other thing we've had to consider is where you would actually put this transmitter on the Green Bank telescope. The proof of concept transmitter was on the prime focus boom at the prime focus. However, a system as large as we want to make with, let's say, 500 kilowatts of output power, it's just too large, too heavy. You can't get the power and the cooling out to the prime focus. So instead, what we want to do is we want to put the hardware down at the main dish level on the side of the feed arm. So this is essentially opposite the elevator system on the Green Bank telescope. We'll have the hardware there, and it would go up to a subreflector at the prime focus. It would illuminate that, reflect down onto the primary surface and out into space. So that's kind of where we are in terms of placing the transmitter. And this will, of course, be a significant infrastructure project at the GBT and VLBA. GBT, you have to have a support structure for the transmitter. You have to build the transmitter. You have to have a subreflector system. You have to get the power and the cooling to both the site and through the telescope, and so on. And then VLBA, this is a bit of a different operational strategy than is usually done with the VLBA. So we'll have to evolve that as we plan out this project. Now, we're not doing this just because we think it sounds cool, and we so there are a lot of community and even federal level feedback that are pushing us in this direction, especially with the loss of the Arecibo telescope a few years ago. Recently, the Planetary Science Decadal Survey came out. That's the Origins, Worlds, and Life report there on the left. And amongst their recommendations were NASA and NSF should review expanded capabilities at existing facilities and try and exceed the capabilities available at Arecibo. So, of course, we have existing facilities at the GBT and the VLBA, so we would be responsive to that recommendation in terms of expanding the capabilities at those facilities. And it's not just the scientific community. There's also two strategies and action plans that are coming out of essentially the White House from the Executive Office of the President. There's one study or one plan called the National Near-Earth Object Preparedness Strategy and Action Plan. And the top level action in that plan is to identify options in existing and planned telescope programs to improve detection and tracking. And this includes radar facilities. So again, Green Bank and VLBA, and eventually the next generation Very Large Array, ngVLA, could be applied to this as being responsive through opportunities to use existing and planned telescope programs. And finally, there's something called the National Cislunar Science and Technology Strategy. One of their key objectives is to extend US space situational awareness capabilities into cislunar space. And they do note that this has obvious synergies with the work done with planetary science and planetary defense. Essentially, if you have an objective you want to do for planetary defense, any system that can meet that objective should meet the objectives for cislunar space situational awareness. So that's the synergy there. So we feel this project is responsive to all of these. And one final note, there was something called the Cross-Disciplinary Deep Space Radar Needs Study. So this was sort of an offshoot of that recommendation from the Planetary Science Decadal Survey for NASA and NSF to study the future of planetary radar. So this report was done by the Aerospace Corporation on behalf of NASA, NSF, and other stakeholders to try and identify the needs for a national radar system or facility. And in their summary in this report, they noted that a high-power radar on the Green Bank telescope could potentially provide the capabilities desired by several stakeholders. So the main things they were looking at were planetary defense objectives and the cislunar situational awareness objectives. And they found that Green Bank, especially if you tie it to the next generation VLA as a very powerful receiver in the future, you would be able to meet a lot of the objectives set out for planetary defense and situational awareness. So essentially, they looked at a couple different solutions: near term, midterm, and far term. Near term was essentially the status quo of Goldstone being the only real planetary radar system. Midterm being something like Green Bank and the next generation Very Large Array, where you're using existing and planned telescope facilities for radar. And then a far term solution where you build a completely new dedicated transmit and receive array for planetary radar. And essentially what they found was the midterm option, meaning the Green Bank telescope and the ngVLA, could be very attractive if funding was available from stakeholders to develop, construct, and operate those systems. Just for reference, the far-term solution, if we tried to build a new dedicated planetary radar transmit and receive array, you would have to expect that to cost somewhere in the $1 to $2 billion range. So a comparison would be essentially building an additional ngVLA scale facility, or essentially sacrificing a new frontiers spacecraft mission. That's sort of the level of cost and involvement you would need. So, so the option of using GBT as a transmitter and ngVLA in the future as a receiver is very attractive. And the first step to getting to that point is the GBT VLBA system that I've described so far. So I think I will end there. Hopefully I've kind of given you an idea where we are with this project and how it could be very responsive to the needs of the community and the nation in the future. So thank you.
Much, Patrick. We have time for just one question, and we have a question. Are there facilities other than the VLBA that would be able to receive echoes from GBT radar transmissions?
Yeah, there's nothing that necessarily restricts it to just the VLBA. If you have a KU band receiver in that sort of 13.7 gigahertz range, you could certainly receive the signals. Of course, you just need to have overlapping visibility between the GBT site and whatever your site might be.
Mm-hmm. And Tom, let me squeeze one more quick question in. Are there any plans to improve the 30-year-old KU band VLBA receivers?
That is a good question. I don't have a good answer for you. There may be others in the audience that might be able to answer that better than I can right now.
Well, please submit answers through the chat window then. I'm afraid that's all the time we have today. Thanks very much, Patrick, for a most interesting talk. And again, you can view this talk in a day or so through the Green Bank Observatory website. Please join us 2 weeks from now on April 10th, when Qian Law will be speaking about polarized light from massive protoclusters. We hope to see you then. Thanks and goodbye.
One quick note here at the end, folks. Questions that were submitted in the Q&A and were not able to be answered live on air, I will be submitting those questions to Patrick so he can follow up on those as needed. Thank you very much and have a good day.